Hello there, and welcome to the Scientist Sleepy. Tonight, we embark on a gentle exploration, a quiet dive into one of the universe's most profound and perplexing enigmas. What truly lies within a black hole? We'll be venturing beyond the familiar concepts, unraveling the illusion of spacetime, and contemplating the very fabric of reality as we understand it. Prepare for a calm lecture, a journey into the extraordinary, where the ordinary rules of existence seem to bend and reshape. Let us begin our drift. The event horizon is a point of no return. Imagine, if you will, standing at the very edge of a cosmic abyss. This isn't just any abyss. It's the boundary of a black hole, a place where the familiar rules of our universe begin to bend, and then spectacularly break. This boundary, this enigmatic threshold, is known as the event horizon. It's not a physical wall you can touch or see in the traditional sense. Instead, it's a region of spacetime where gravity becomes so overwhelmingly powerful that nothing, not even light itself, can escape its relentless pull. Think of it as a one-way membrane, a cosmic veil separating our observable universe from the unfathomable mystery that lies within. To truly grasp the significance of the event horizon, we must first appreciate the immense gravitational force at play. Black holes are born from the catastrophic collapse of massive stars. When a star much larger than our Sun exhausts its nuclear fuel, its core can no longer withstand the inward crush of its own gravity. It implodes, compressing an enormous amount of mass into an incredibly small volume. This extreme density is what generates the profound gravitational field characteristic of a black hole. As you approach this region of intense gravity, spacetime itself begins to distort. Imagine spacetime as a vast, flexible fabric. A massive object like a star creates a dip in this fabric. A black hole, however, creates an infinitely deep well. The event horizon marks the precise point where this gravitational well becomes so steep that the escape velocity, the speed needed to break free from the gravitational pull, exceeds the speed of light. Since, according to Einstein's theory of relativity, nothing can travel faster than light, anything that crosses this boundary is irrevocably trapped. It's like sailing past the point of no return in a river that flows towards a colossal waterfall. Once you've passed that critical point, no amount of rowing, no matter how powerful, can bring you back upstream. The current is simply too strong. This concept has profound implications for our understanding of cause and effect, and even the nature of time. For an observer safely distant from the black hole, time appears to flow normally. However, for someone or something venturing closer, time begins to stretch and slow down relative to the distant observer. As an object approaches the event horizon, its time would appear to crawl to a complete standstill from the perspective of someone far away. Conversely, for the unfortunate traveler, their journey towards the event horizon would seem to happen in a finite amount of their own time, albeit under increasingly bizarre conditions. It's important to understand that the event horizon is not a static, invisible barrier that suddenly appears. It's an intrinsic property of the black hole's mass and spin. For a non-rotating black hole, this boundary is a perfect sphere. For a rotating black hole, the situation becomes more complex, with the horizon taking on a more oblate shape. But the fundamental principle remains. Cross this line, and you are on a path from which there is no deviation, no escape, and no return to the universe you once knew. The information about what happens beyond this point is effectively lost to the outside universe, leading to deep questions in physics. The event horizon, therefore, serves as the ultimate cosmic frontier, a boundary beyond which our current scientific models struggle to provide definitive answers. It is the silent guardian of the black hole's inner secrets, a testament to the extreme power and enigmatic nature of gravity in the cosmos. The edge of forever, where even light surrenders, whispers of a journey from which no echo returns. Singularity is where our current physics breaks down. Imagine, if you will, venturing towards the heart of a black hole, past the point of no return, the event horizon. As you draw closer, the very fabric of reality, the interwoven tapestry of space and time, begins to contort and twist in ways that defy our everyday intuition. The gravitational pull becomes so immense, so concentrated, that our established laws of physics, the very tools we use to understand the universe, start to falter. This is the realm of the singularity. At its core, a black hole is thought to contain a singularity, a point of infinite density and zero volume. This is not a physical place in the way we understand places, but rather a state where our current models of the universe, governed by both general relativity and quantum mechanics, cease to provide coherent answers. General relativity, Einstein's groundbreaking theory of gravity, predicts that all matter falling into a black hole will be crushed into an infinitely small point at its center. This is the singularity. However, the concept of infinity in physics is often a sign that our theories have reached their limit. Infinity implies a breakdown in predictability, a point where our equations yield nonsensical results, such as division by zero. When we talk about infinite density, we are describing a situation where a finite amount of mass is squeezed into an infinitesimally small space. This is a concept that our minds, accustomed to the finite and the measurable, struggle to grasp. Quantum mechanics, the theory that describes the universe at the smallest scales, also presents challenges when confronted with the extreme conditions of a singularity. At such incredibly high densities and energies, quantum effects are expected to become dominant. Yet, general relativity, which describes gravity on the grandest scales, does not readily incorporate quantum principles. The singularity is a boundary where these two pillars of modern physics, general relativity and quantum mechanics, seem to be at odds, unable to provide a unified description. Scientists believe that a new, more comprehensive theory, often referred to as a theory of quantum gravity, is needed to truly understand what happens at the singularity. Such a theory would aim to reconcile the behavior of gravity with the principles of quantum mechanics, offering a complete picture of the universe from the smallest subatomic particles to the largest cosmic structures. The very idea of a singularity challenges our fundamental understanding of space and time. In general relativity, spacetime is a dynamic entity, warped by mass and energy. Near a singularity, this warping becomes so extreme that the concepts of distance and duration, as we know them, lose their meaning. It is a region where the rules that govern our observable universe no longer apply. Some theories propose that the singularity might not be a point of infinite density at all, but rather a region where spacetime itself is so fundamentally altered that our current language and mathematical tools are inadequate to describe it. Perhaps it is a gateway to another dimension, or a region where spacetime is so heavily quantized that it becomes discrete rather than continuous. The quest to understand the singularity is one of the most profound challenges in theoretical physics. It pushes the boundaries of our knowledge and forces us to question the very nature of reality. While we may not be able to directly observe what lies at the heart of a black hole, the pursuit of this understanding drives innovation and deepens our appreciation for the mysteries that the cosmos holds. The singularity, in its enigmatic nature, serves as a constant reminder of the vastness of our ignorance and the endless frontier of scientific discovery. It is a place where our current understanding dissolves, beckoning us to seek new paradigms, to dream of theories yet unimagined, and to accept that some of the universe's most profound truths may lie beyond our current grasp, in realms where our familiar physics no longer holds sway. The breaking of our known laws at the singularity whispers that reality's deepest secrets reside in the profound unknown. Spacetime warps dramatically near a black hole. Imagine space and time not as a rigid, unchanging stage, but as a flexible, dynamic fabric. This is the profound insight of Einstein's theory of general relativity. Gravity, in this view, isn't a mysterious force pulling objects together, but rather the curvature of this spacetime fabric itself. And when we speak of black holes, we are speaking of the most extreme manifestations of this curvature. Near a black hole, the fabric of spacetime is not just gently bent, but violently distorted, twisted, and stretched to an almost unimaginable degree. Think of placing a bowling ball on a stretched rubber sheet. It creates a dip. Now, imagine that dip becoming infinitely deep, so deep that anything falling in can never climb back out. That's a simplified analogy for the warping of spacetime around a black hole. The closer you get to a black hole, the more pronounced this warping becomes. For an observer far away, spacetime might appear relatively normal, even if there's a massive black hole lurking in the cosmic distance. But for an astronaut venturing nearer, the effects would become astonishingly apparent. Distances would appear to stretch and compress in peculiar ways. Paths that should be straight would become curved, not by a force, but by the very geometry of space itself. This warping affects not just space, but time as well. According to general relativity, time is inextricably linked to space, forming a unified entity called spacetime. Gravity, or the curvature of spacetime, influences the passage of time. The stronger the gravitational field, the slower time passes. Near a black hole, where gravity is immense, time dilation becomes extreme. If you were to hover just outside the event horizon of a black hole, time for you would tick by much slower than for someone on Earth. A few minutes for you could translate into years, even centuries back home. This isn't a trick of perception. It's a fundamental alteration of the flow of time itself, dictated by the extreme geometry of space-time. The very concept of a straight line, a geodesic, becomes profoundly altered. In flat spacetime, a geodesic is the shortest path between 2 points. But in the curved spacetime around a black hole, geodesics are no longer straight. They bend and twist in response to the intense gravitational pull. Light, which always travels along geodesics, follows these curved paths. This is why we observe gravitational lensing, where the light from distant stars and galaxies is bent as it passes near massive objects, including black holes, making them appear in distorted or multiple images. The warping is so severe that it eventually leads to the formation of the event horizon, the boundary beyond which escape is impossible. The event horizon isn't a physical surface, but rather a region in space-time where the curvature becomes so extreme that all possible paths, all geodesics, lead inward towards the singularity. Even light, the fastest thing in the universe, cannot outrun the relentless inward pull of this warped space-time. The mathematical description of this warping is complex, often involving tensors and differential geometry. But the core idea is that mass and energy dictate the curvature of spacetime, and this curvature, in turn, dictates how mass and energy move. A black hole, being an incredibly dense concentration of mass, creates an unparalleled distortion. It's as if spacetime itself has been stretched and folded in on itself to an extreme degree, creating a cosmic abyss from which there is no return. The dramatic warping of spacetime near a black hole is a testament to the universe's ability to bend the very fabric of existence. The fabric of reality warps and bends, a cosmic dance orchestrated by gravity's profound embrace. Light itself cannot escape a black hole's gravity. Imagine, if you will, a cosmic scenario so extreme, so profoundly influential that it redefines the very fabric of our universe. This is the realm of black holes, and at their heart lies a principle that challenges our everyday intuition: the absolute inability of light, the fastest thing in existence, to break free from their gravitational embrace. To truly grasp this, we must first appreciate the immense power of gravity. On Earth, gravity pulls us down, keeping our feet firmly planted. It's a force that governs the orbits of planets around stars and stars within galaxies. But near a black hole, gravity is not merely strong, it is absolute. It is a distortion so severe, so all-encompassing, that it creates a boundary, a one-way membrane in the universe. This boundary is known as the event horizon. The event horizon is not a physical surface you could touch or see in the traditional sense. Instead, it is a conceptual limit, a point in spacetime where the escape velocity, the speed required to overcome a gravitational pull, equals the speed of light. Think of it like trying to throw a ball upwards on Earth. If you throw it with enough speed, it will escape Earth's gravity and fly into space. But if you don't throw it fast enough, it will eventually fall back down. Now, imagine a place where the gravitational pull is so immense that even if you could throw that ball at the speed of light, it would still fall back. That is the essence of the event horizon. Light, composed of photons, travels at a constant speed in a vacuum, approximately 299,792 kilometers per second. This is the universal speed limit, the fastest anything can possibly move. When light encounters a black hole, it behaves like any other form of matter or energy in its vicinity. It is drawn in by the overwhelming gravity. If the light is far enough away from the black hole, it can indeed orbit or even escape, just as planets orbit stars. However, once a photon crosses the event horizon, its fate is sealed. The spacetime within the event horizon is so warped that all possible paths, all trajectories, lead inevitably towards the center of the black hole, towards the singularity. It's not that the light itself loses speed or energy in a way we might intuitively understand. Rather, the very geometry of spacetime within the event horizon is bent so severely that all directions point inwards. Imagine being in a river flowing towards a waterfall. Even if you swim with all your might, the current is so strong that you are carried downstream. The event horizon is like the point where the current becomes too powerful to resist, and the waterfall is the singularity. The concept of light being trapped is central to why black holes are called black. Since no light can escape from within the event horizon, we cannot see what lies beyond it. Any light that falls in is effectively removed from our observable universe. This is why black holes appear as dark regions in space, even though they are regions of immense gravitational influence. The only way we can detect them is by observing their effects on their surroundings, such as the swirling accretion disks of superheated gas and dust that orbit them, or the gravitational lensing they cause on light from more distant objects. The fact that light, the messenger of the cosmos, cannot escape from within a black hole underscores the profound and alien nature of these celestial objects. It signifies a boundary beyond which our current understanding of physics struggles to provide definitive answers, a place where the familiar rules of the universe are dramatically rewritten by the sheer power of gravity. It is a testament to the mind-bending possibilities that exist within the vast expanse of the cosmos, a reminder that reality can often be far stranger and more wondrous than we can easily imagine. And so, the light that enters is forever held, a silent testament to gravity's ultimate dominion. Time slows to a crawl for an observer near a black hole. Imagine, if you will, a cosmic clock its steady tick marking the relentless march of moments. Now picture that clock brought into the extreme gravitational embrace of a black hole. What happens to its rhythm? It doesn't just slow down, it stretches, warps, and nearly grinds to a halt, at least from the perspective of someone watching from afar. This profound phenomenon is a direct consequence of Einstein's theory of general relativity, specifically the concept of gravitational time dilation. Gravity, as we understand it, is not a force in the traditional sense, but rather a curvature of spacetime. Massive objects like stars and planets create dips and valleys in this fabric, and black holes, with their immense density, create the deepest, most extreme wells imaginable. When you approach a region with incredibly strong gravity, the very fabric of spacetime is so distorted that it affects the passage of time itself. For an observer who is far away from a black hole, watching a brave hypothetical astronaut venture closer, their clock would appear to tick slower and slower as they approach the event horizon. If this astronaut were to send a light signal back every second, according to their own watch, the distant observer would receive those signals at increasingly longer intervals. The closer the astronaut gets to the point of no return, the more pronounced this effect becomes. At the event horizon itself, from the perspective of the distant observer, time for the astronaut would appear to stop entirely. They would seem frozen in that moment, forever on the precipice of the unknown. However, this is a crucial distinction. The astronaut asterisk themselves would not feel time slowing down. Their own biological processes, their own watch, would continue to function normally from their frame of reference. They would not perceive any change in the rate at which time passes for them. The dilation is relative. It's a difference observed between two frames of reference in different gravitational potentials. The universe, in its magnificent complexity, orchestrates these temporal discrepancies, a subtle reminder that our experience of time is not an absolute, universal constant, but a fluid aspect of the cosmic dance. The extreme gravity of a black hole is a stark demonstration of this, a place where the very rhythm of existence is profoundly altered, a testament to the interconnectedness of mass, energy, and the flow of time. It's a profound illustration of how gravity shapes not just space, but the very essence of duration, stretching moments into eternities from an outside vantage point. This temporal distortion is not just a theoretical curiosity, it's a fundamental prediction of our most successful models of the universe, a prediction that continues to shape our understanding of the cosmos and our place within it. The closer one ventures to such a gravitational behemoth, the more profound the divergence in temporal experience becomes, a silent testament to the universe's capacity for the utterly extraordinary. And in this cosmic slowdown, we find a profound stillness, a reminder that even in the most extreme environments, time itself bows to the grand architecture of existence. Tidal forces would stretch an object to oblivion. Imagine an object, perhaps a small probe, venturing too close to the invisible maw of a black hole. As it approaches, a peculiar and terrifying force begins to act upon it. This is not a uniform pull, like the gentle embrace of Earth's gravity. Instead, it's a differential force, a stretching and squeezing that intensifies with proximity. This phenomenon is known as tidal force, and near a black hole it becomes unimaginably powerful. The reason for this extreme effect lies in the incredibly steep gravitational gradient. The side of the object closer to the black hole experiences a vastly stronger gravitational pull than the side farther away. This disparity creates a powerful stretching effect along the direction of the black hole. Simultaneously, there's a crushing force from the sides. Think of it like being squeezed from all directions, while being pulled apart from head to toe. For a star, this might manifest as a dramatic distortion, its gaseous form being drawn out into long, filamentary streams that spiral into the black hole. For a solid object like our hypothetical probe, the effect would be even more catastrophic. The materials themselves would be torn apart at an atomic level. This process has been given a rather evocative and accurate name: spaghettification. It's a vivid description of how matter is elongated into a thin, string-like form before being completely consumed. The intensity of these tidal forces depends on the mass of the black hole. For smaller, stellar mass black holes, these forces are incredibly strong even outside the event horizon, meaning an object would be spaghettified before it even reached the point of no return. For supermassive black holes, found at the centers of galaxies, the tidal forces are much weaker at the event horizon. This is because the gravitational gradient is much gentler due to the immense size. An astronaut could, theoretically, cross the event horizon of a supermassive black hole without immediately feeling these destructive forces. However, the journey inward would eventually lead to the singularity, where the forces become infinite and oblivion is assured. The stretching and squeezing, the spaghettification, is a direct consequence of the fundamental nature of gravity as described by general relativity. It's a stark reminder that the universe, in its most extreme environments, operates by principles that can be both awe-inspiring and terrifyingly destructive. The very fabric of spacetime, warped to such an extreme degree, dictates the ultimate fate of anything that dares to venture too close. It's a testament to the universe's power, a silent testament written in the distorted remnants of matter. In the cosmic ballet of gravity, even the most robust forms are rendered as ephemeral threads, woven into the infinite by forces beyond comprehension. The Schwarzschild radius defines the event horizon size. Imagine, if you will, a cosmic scale, a theoretical ruler that can measure the very boundary of a black hole's influence. This boundary, the point of no return, is not an arbitrary line drawn in the cosmic dust. It is, in fact, precisely defined by a fundamental concept known as the Schwarzschild radius. This radius is not a fixed physical object, but rather a calculated distance, a spherical shell around the black hole's center, beyond which nothing, not even light, can escape. It is named after the brilliant German physicist Karl Schwarzschild, who, in the midst of the First World War, derived a solution to Einstein's field equations for general relativity that described the gravitational field outside a non-rotating, spherically symmetric mass. This solution revealed a profound truth, that for any given mass, there exists a critical radius. If all of that mass were compressed within this radius, it would collapse into a black hole. The event horizon, that intangible yet absolute barrier, would then coincide precisely with this Schwarzschild radius. The size of this radius is directly proportional to the mass of the object. A more massive object will have a larger Schwarzschild radius, and thus a larger event horizon. For our Sun, if it were to somehow collapse into a black hole, its Schwarzschild radius would be a mere 3 kilometers. For the supermassive black hole at the center of our Milky Way galaxy, Sagittarius A, which has a mass about 4 million times that of our Sun, the Schwarzschild radius is approximately 12 million kilometers. This is still a vast distance, far larger than the Sun itself, but it gives us a sense of the scale involved. It's crucial to understand that the event horizon is not a surface in the conventional sense. You wouldn't feel a jolt, or a wall, or any physical resistance as you crossed it. It is, instead, a geometric property of spacetime itself, a consequence of extreme gravitational warping. Once you cross this invisible threshold, the fabric of spacetime is so distorted that all possible future paths lead inexorably towards the singularity at the center. There is no outward direction to travel. The very concept of outside ceases to exist for anything that has ventured within. The Schwarzschild radius, therefore, is the ultimate cosmic perimeter, the precise measure of the gravitational embrace from which escape is mathematically and physically impossible. It is the quiet, invisible marker of a realm where the familiar rules of our universe are fundamentally rewritten. And so, the Schwarzschild radius marks the silent, invisible edge of ultimate gravity, a reminder that even the void has its meticulously defined boundaries. Hawking radiation suggests black holes aren't entirely black. Even the most seemingly absolute phenomena in the universe can hold surprising nuances, and black holes, often perceived as ultimate voids, are no exception. For a long time, the prevailing understanding was that once something crossed the event horizon, it was gone forever, contributing to the black hole's mass and remaining eternally within its gravitational embrace. However, the brilliant mind of Stephen Hawking, through the lens of quantum mechanics and general relativity, introduced a concept that fundamentally challenged this notion: Hawking radiation. This profound idea suggests that black holes are not entirely black, and in fact, they can slowly lose mass and energy over incredibly vast timescales. The mechanism behind this radiation is a fascinating interplay of quantum vacuum fluctuations near the event horizon. In empty space, particles and antiparticles are constantly popping into existence and annihilating each other in pairs, a phenomenon known as quantum vacuum fluctuations. It's as if the fabric of spacetime is perpetually bubbling with ephemeral existence. Now, imagine this happening right at the edge of a black hole, at the event horizon. Sometimes, a particle-antiparticle pair can be created so that one particle falls into the black hole while the other escapes. To an outside observer, it appears as if the black hole is emitting particles, carrying away energy and mass. Because the particle that falls in has negative energy relative to the outside universe, its entry into the black hole effectively reduces the black hole's total mass. The escaping particle, then, is the Hawking radiation. This process is incredibly slow for stellar mass or supermassive black holes. The energy required to create these particle pairs is enormous, and the rate at which they are produced is minuscule compared to the black hole's immense gravity. For a black hole with the mass of our Sun, it would take vastly longer than the current age of the universe for it to evaporate completely through Hawking radiation. However, for hypothetical smaller black holes, perhaps formed in the early universe, this evaporation process could be much more rapid, potentially even leading to a final, energetic burst as they reach the end of their existence. This concept is not just a theoretical curiosity, it has profound implications for our understanding of physics. It bridges the gap between general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of particles at the smallest scales. The information paradox, a major puzzle in physics, also touches upon Hawking radiation. If a black hole evaporates entirely, what happens to the information contained within the matter that fell into it? Quantum mechanics dictates that information cannot be destroyed, but general relativity suggests that once information crosses the event horizon, it is lost to the outside universe. Hawking radiation offers a potential, albeit complex, pathway for information to escape, though the exact mechanism remains a subject of intense debate and research. It suggests that the black hole's final moments might carry clues about its history, a faint echo of everything it has ever consumed. Ultimately, Hawking radiation paints a picture of black holes not as static, eternal prisons, but as dynamic entities slowly fading into the cosmic background, a testament to the universe's persistent, subtle, and ever-evolving nature. Like whispers of existence in the void, These faint emissions remind us that even the darkest corners of the cosmos are touched by the gentle hum of creation and eventual release. Information paradox questions what happens to lost data. Imagine, if you will, a fundamental principle in the universe that underpins all our understanding of physics: the conservation of information. This isn't just about keeping secrets. It's about the idea that the fundamental properties of matter and energy are never truly lost. They might transform, they might scatter, but they can, in principle, always be traced back. This principle is deeply ingrained in quantum mechanics, the realm of the very small. Now, introduce a black hole. According to classical general relativity, anything that crosses the event horizon is gone forever, its information seemingly erased from the observable universe. When a black hole eventually evaporates through Hawking radiation, it's thought to emit thermal radiation, a kind of generic glow that doesn't seem to carry any specific information about what fell in. This is where the paradox arises. If information truly disappears into a black hole and is not returned when the black hole evaporates, then this core principle of quantum mechanics is violated. It's as if the universe has a cosmic trash can where data goes to die, a concept that deeply unsettles physicists. Stephen Hawking himself grappled with this paradox for decades, acknowledging that it pointed to a fundamental misunderstanding of how gravity and quantum mechanics interact at the extreme conditions found within and around black holes. Various proposed solutions have emerged, each attempting to reconcile this apparent conflict. Some suggest that the information isn't lost, but is somehow encoded in the Hawking radiation itself, perhaps in subtle correlations that are incredibly difficult to detect. Others propose that the information might be preserved in remnants left behind after evaporation, or even that it might be transferred to another universe. The very nature of what constitutes information in such extreme environments is also debated. Is it the specific arrangement of particles, their quantum states, or something more abstract? The information paradox highlights the profound limitations of our current theoretical frameworks. It suggests that a complete theory of quantum gravity, one that successfully unifies general relativity and quantum mechanics, is essential to truly understand the fate of matter and energy in the most enigmatic objects in the cosmos. It forces us to question our very assumptions about causality, the flow of time, and the ultimate nature of reality itself. The quest to resolve this paradox is not merely an academic exercise. It's a deep dive into the fundamental laws that govern existence, pushing the boundaries of our comprehension and hinting at a universe far stranger and more interconnected than we can easily imagine. It's a profound reminder that even in the face of seemingly absolute destruction, the universe may hold onto its secrets in ways we have yet to uncover. The echoes of what falls into the void may whisper in the starlight of what remains. Black holes may not be singularities, but fuzzballs. For a long time, our most cherished and perhaps most terrifying vision of the interior of a black hole was the singularity, an infinitely dense point where all the mass of the collapsed star is crushed into a space of zero volume. This is the stark prediction of Einstein's theory of general relativity, a point where spacetime curvature becomes infinite, and our familiar laws of physics simply cease to apply. It's a concept that has fueled countless science fiction stories and philosophical debates, a true abyss at the heart of reality. However, as our understanding of physics deepens, particularly through the lens of quantum mechanics, this stark singularity may be an oversimplification or even an illusion. A compelling alternative model, known as the fuzzball theory, proposes that the event horizon of a black hole isn't a sharp, distinct boundary leading to an infinite point, but rather a complex, quantum mechanical surface. Imagine, if you will, that the entire region within the event horizon is not empty space leading to a singularity, but is instead a vibrant, turbulent, and incredibly intricate quantum state. In this fuzzball picture, the black hole is not a simple void but a highly energetic and complex object, much like a tangled ball of string, but made of fundamental quantum constituents. These constituents, perhaps strings or other quantum entities, are arranged in a way that creates the illusion of a singularity and an event horizon. Instead of a single point of infinite density, the fuzzball model suggests that the mass and energy are spread out over a vast, quantum mechanical structure that extends throughout the interior of what we perceive as the black hole. The event horizon in this view is not a surface of no return in the classical sense, but rather the outer boundary of this quantum fuzz. It's where the probability of finding these quantum constituents becomes so high that it effectively mimics the behavior of a classical event horizon. This doesn't negate the extreme gravitational effects or the inability of anything to escape once it crosses this boundary, but it reframes the fundamental nature of what lies within. The fuzzball theory attempts to resolve some of the long-standing paradoxes associated with black holes, such as the information paradox. If a black hole is a singularity, information about what fell into it seems to be irretrievably lost, violating a fundamental principle of quantum mechanics. But if the black hole is a fuzzball, a complex quantum object, then the information might be encoded within its intricate structure, perhaps even being released gradually through Hawking radiation in a way that preserves it. This is a profound shift in perspective. It suggests that the inside of a black hole is not a simple, empty void leading to an infinite point, but a realm of immense quantum complexity, a universe of its own, albeit one utterly alien to our everyday experience. The fuzzball theory, still an area of active research and debate, offers a tantalizing glimpse into a universe where the extremes of gravity and quantum mechanics meet, blurring the lines between the known and the unknowable, and suggesting that even in the darkest, most enigmatic corners of the cosmos, there is a rich and complex reality at play. The idea of a singularity, while mathematically elegant in certain contexts, may be a signpost that our current theories are incomplete, a placeholder for a deeper, more nuanced understanding that emerges when we dare to imagine the impossible. The fuzzball model, with its quantum intricacies, paints a picture of a black hole as a vibrant, albeit incomprehensible quantum entity, rather than a simple cosmic drain. It is a testament to the fact that even the most abstract concepts in physics can lead to profound and beautiful reinterpretations of reality, reminding us that the universe is far more wondrous and complex than we can initially conceive. The very notion of inside and outside may become fluid, and the boundary we perceive may be a manifestation of a far grander quantum tapestry. The universe, in its most extreme forms, may be a tapestry of quantum complexity, where even the deepest voids hold the secrets of existence. The illusion of spacetime is created by extreme gravity. Imagine, if you will, the very fabric of existence, space and time, not as rigid, unchanging entities, but as a dynamic, pliable tapestry. This is the profound insight gifted to us by Einstein's theory of general relativity. It tells us that what we perceive as gravity, that invisible force that pulls apples to the earth and keeps planets in orbit, is not a force in the traditional sense at all. Instead, it is the curvature, the warping, the very distortion of this spacetime fabric caused by the presence of mass and energy. Think of it like placing a heavy bowling ball onto a stretched rubber sheet. The sheet dips and curves around the ball. Now, if you were to roll a small marble across that sheet, it wouldn't travel in a straight line. It would curve towards the bowling ball, following the dip in the sheet. This, in essence, is how gravity works. Mass tells spacetime how to curve, and the curvature of spacetime tells mass how to move. Now, when we consider the extreme conditions found near a black hole, this warping becomes not just significant, but utterly mind-bending. The sheer concentration of mass within a black hole's incredibly small volume creates a gravitational pull so immense that it warps spacetime to an unimaginable degree. It's like taking that rubber sheet and placing an object of infinite density at its center. The sheet would be stretched, pulled, and distorted to its absolute limit, creating a profound, almost bottomless well. This extreme curvature is what creates the illusion of spacetime as we might intuitively understand it. For an observer far away, spacetime might appear relatively flat, with objects moving along predictable paths. But as you approach the black hole, the fabric itself begins to bend and twist in ways that defy our everyday experience. Time, for instance, doesn't flow at a constant rate for everyone. Near a black hole, time slows down dramatically relative to an observer in a weaker gravitational field. This isn't a trick of perception. It's a fundamental alteration of the temporal dimension itself, a direct consequence of spacetime being so severely warped. The very concept of distance and direction also becomes distorted. What appears as a straight path to a distant observer might be a spiraling descent into the gravitational abyss for someone closer. The illusion, therefore, is not that gravity isn't real, but that our perception of space and time as separate, absolute, and unchanging is an approximation that breaks down under the crushing influence of extreme gravitational fields. The black hole doesn't just exert a force. It fundamentally reshapes the arena in which all physical phenomena occur, creating a reality where space and time are inextricably linked and dynamically sculpted by the presence of extreme mass. This warping is so profound that it defines the very boundary of the black hole, the event horizon, beyond which escape becomes impossible because the very structure of spacetime itself is pulling everything inward. It is in these extreme environments that the universe reveals its most astonishing truths about the nature of reality, showing us that space and time are not passive backdrops, but active participants in the cosmic dance, their forms dictated by the grandest architects of gravity. The universe, in its most extreme manifestations, teaches us that our familiar notions of space and time are but gentle ripples on an ocean of cosmic curvature, an illusion woven by the very fabric of existence when it is stretched to its most profound limits. In the crushing embrace of a black hole, the very stage of existence is bent and reshaped, revealing that our familiar sense of space and time is merely a gentle whisper in the face of cosmic gravity's profound symphony. Our understanding of inside becomes meaningless. The very notion of inside, a black hole, as we typically understand it, dissolves into an enigma that defies our everyday intuition and the familiar laws of physics. When we speak of inside, a house, a box, or even our planet, we refer to a region bounded by a surface, a place we can theoretically occupy and interact with. But a black hole, particularly beyond its event horizon, is a realm where these concepts simply cease to apply. The event horizon itself is not a physical barrier, but rather a boundary in spacetime. Once crossed, all paths, including those of light, lead inexorably towards the central singularity. There is no sideways, no backwards, and certainly no out. The very fabric of spacetime, so warped and distorted, means that the future direction for anything that has fallen in is always towards the singularity. To ask what it's like inside is akin to asking what is north of the North Pole. The question itself is framed by a geometry that no longer holds. Our three-dimensional understanding of space and time, so effective in our familiar universe, becomes inadequate, perhaps even misleading, when applied to the extreme curvature and density found within a black hole. Physicists grapple with this by employing mathematical frameworks that can describe such extreme conditions, often involving general relativity and quantum mechanics. But the lived experience, if such a thing were even possible without immediate destruction, would be utterly alien. The internal structure, if it can even be called that, is not a space to be explored in the conventional sense, but a state of being, or rather, a process leading to an ultimate, unknown end. The singularity, where our current understanding of physics breaks down, represents the ultimate limit to our ability to define an inside. It's a point of infinite density and zero volume, a concept that strains our capacity for visualization. Some theories suggest that the singularity might not be a point at all, but a region where spacetime itself is fundamentally altered, perhaps even creating a gateway to another universe or a new phase of existence. However, any information about this hypothetical inside is irrevocably cut off from us by the event horizon. The very act of observation, of trying to perceive what lies within, would require sending a signal that could never return. Thus, the inside of a black hole becomes a philosophical and scientific construct, a placeholder for the unknown, rather than a tangible location. Our language, built upon our experiences in a relatively flat and predictable spacetime, fails us here. The universe, in its most extreme manifestations, forces us to question our most fundamental assumptions about reality, space, and time. The black hole serves as a profound reminder of the limits of our current knowledge and the vastness of what remains undiscovered, a cosmic enigma that challenges the very foundations of our perception. The interior is not a place one visits, but a state of being that exists beyond our comprehension, a testament to the universe's boundless capacity for mystery. In this cosmic abyss, where our familiar maps of existence dissolve, the concept of inside becomes a whisper lost in the grand, silent hum of the unknown. Quantum mechanics and general relativity clash here. Here, at the heart of a black hole, the two pillars of modern physics, quantum mechanics and general relativity, find themselves in a profound and irreconcilable disagreement. For decades, scientists have grappled with this cosmic conundrum, a theoretical battlefield where the very fabric of reality is tested. General relativity, Einstein's elegant description of gravity, paints a picture of smooth, continuous spacetime, warped and curved by mass and energy. It excels at describing the large-scale universe, the dance of planets, stars, and galaxies. Quantum mechanics, on the other hand, governs the realm of the very small, the strange and probabilistic world of atoms, subatomic particles, and their interactions. It's a universe of discrete packets of energy, uncertainty, and bizarre entanglement. When we try to apply both theories simultaneously to the extreme conditions within a black hole, specifically at the singularity, they break down. General relativity predicts an infinitely dense point, a place where spacetime curvature becomes infinite, a concept that quantum mechanics struggles to accommodate. Quantum theory suggests that at such incredibly small scales, the smooth continuum of spacetime should break down into discrete, quantized units, much like energy exists in packets. But how these two descriptions merge, or if they can merge at all, remains one of the greatest unsolved mysteries in physics. The singularity of a black hole is a place where our current understanding falters, a boundary beyond which our established laws of physics cease to be reliable guides. It's like trying to use a map of a city to navigate the depths of the ocean. The tools, while powerful in their own domains, are fundamentally unsuited for the task. Physicists are exploring various avenues to reconcile these theories, seeking a theory of everything or quantum gravity that can unify them. Ideas like string theory, which posits that fundamental particles are not point-like, but rather tiny vibrating strings, or loop quantum gravity, which suggests spacetime itself is quantized, offer potential pathways. But for now, the clash at the singularity serves as a stark reminder of the limits of our knowledge, a point where the universe whispers its deepest secrets in a language we are still struggling to decipher. It's a place where the familiar rules of cause and effect, space and time, may no longer apply in the way we intuitively understand them. The very concept of here and now becomes blurred, a testament to the mind-bending nature of these cosmic enigmas. This theoretical conflict is not just an academic exercise. It has profound implications for our understanding of the universe's origins, its ultimate fate, and the fundamental nature of existence itself. The black hole's singularity, in its defiance of our current scientific frameworks, acts as a powerful beacon, guiding us towards new frontiers of discovery, urging us to expand our conceptual horizons and embrace the unknown. It highlights that what we perceive as solid and absolute reality is, at its most extreme, a fragile construct of our current understanding, a placeholder for a deeper, more complex truth. The universe, in its infinite wisdom, presents these paradoxes to stimulate our curiosity and drive us towards a more complete picture of its intricate workings. At the black hole's core, where familiar laws dissolve, the universe hints at a deeper, unified truth waiting to be found. The universe might be holographic, with black holes as key. Imagine for a moment that the reality we perceive, the vast expanse of stars, galaxies, and the very fabric of spacetime, might not be as fundamental as it seems. The idea of a holographic universe suggests that our three-dimensional existence, with its depth and volume, could be an illusion, a projection emanating from a two-dimensional surface, much like a hologram is created from a flat film. This is not science fiction. It's a frontier of theoretical physics, a concept that emerges from the intricate study of black holes and the very nature of information in the cosmos. At the heart of this profound idea lies the black hole itself. When we consider what happens at the event horizon, the boundary beyond which nothing, not even light, can escape, a perplexing question arises. What happens to the information contained within anything that crosses this threshold? According to classical physics, this information seems to be lost forever. However, quantum mechanics, the theory that governs the subatomic world, insists that information cannot be destroyed. This fundamental conflict, known as the black hole information paradox, has led physicists to explore radical new possibilities. One of the most compelling explanations is the holographic principle. This principle, inspired by the study of black holes, posits that the maximum amount of information that can be contained within a region of space is proportional to the area of its boundary, not its volume. This is a profoundly counterintuitive idea. Think about it. Usually, we assume more volume means more capacity for information. But in a holographic universe, the information content of a three-dimensional object like a black hole might be entirely encoded on its two-dimensional surface, its event horizon. So, the seemingly infinite volume of a black hole could, in essence, be stored on its boundary. This implies that the inside of the black hole, the region we imagine to be filled with collapsed matter and a singularity, might not be a distinct, separate space in the way we intuitively understand it. Instead, the experience of the interior could be a consequence of how information is processed and projected from this 2D surface. This is where the key role of black holes comes into play. They are, in a sense, the ultimate information processors. Their event horizons, acting as these information-storing surfaces, provide the observational and theoretical grounds for the holographic principle. If our entire universe is holographic, then the laws of physics we observe in our 3D reality would be analogous to the projected image of a hologram, with the fundamental reality existing on a lower dimensional boundary. This doesn't mean our reality is fake, in a dismissive sense. It means our perception of it might be a projection. The universe in this view is not a collection of objects occupying volume, but rather a vast, interconnected network of information, with black holes serving as crucial points where this information is compressed and potentially projected. This concept challenges our deepest intuitions about space, time, and existence, suggesting that the universe is far stranger and more interconnected than we might ever have imagined, with the very boundaries of reality holding the secrets to its nature. It's a humbling thought that the most extreme objects in the cosmos might hold the keys to understanding the fundamental structure of existence itself, hinting that the vastness we perceive might be a reflection of something far more subtle and profound, etched onto the very edges of cosmic phenomena. The universe's deepest truths may be etched not in its volume, but on its boundaries, a profound reflection of existence itself. Spaghettification is a dramatic, yet accurate description. Imagine, if you will, an object, perhaps a star, or even an unwary astronaut, venturing too close to the immense gravitational embrace of a black hole. As this object approaches, the force of gravity doesn't act uniformly across its entire form. The part of the object closest to the black hole experiences a significantly stronger pull than the part furthest away. This differential in gravitational force, this stretching sensation, is what scientists have aptly, and perhaps a little dramatically, termed spaghettification. It's a vivid mental image, isn't it? The idea of being stretched thinner and thinner, like a strand of pasta, until you are elongated beyond recognition. This isn't mere hyperbole. It's a direct consequence of the extreme curvature of spacetime and the relentless nature of gravity at its most potent. The physics behind spaghettification is rooted in Newton's law of universal gravitation, which, while a classical approximation, provides a clear understanding of this phenomenon. The force of gravity between two objects is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. When an object is large enough, or the gravitational gradient is steep enough, as it is near a black hole, the difference in gravitational force experienced by different parts of that object becomes immense. Let's consider an astronaut falling feet first towards a black hole. Their feet, being closer to the black hole, will be pulled with far greater force than their head. This disparity in pull will cause the astronaut to stretch longitudinally, elongating their body. Simultaneously, because the gravitational field lines are converging towards the center of the black hole, the sides of the astronaut's body will be squeezed inwards. This combined effect of stretching and squeezing is what leads to the transformation into a long, thin strand. The intensity of spaghettification depends on the size of the black hole. For smaller, stellar mass black holes, which are typically a few times the mass of our Sun, the tidal forces are incredibly strong, and spaghettification would occur well outside the event horizon. An object would be torn apart long before it even had a chance to cross that boundary. However, for supermassive black holes, those millions or even billions of times the mass of our Sun, the gravitational gradient at the event horizon is much gentler. This means that an object, or even an astronaut, could potentially cross the event horizon without immediately being spaghettified. They might survive the initial passage, only to face the inevitable stretching as they journey deeper into the black hole's interior, where the gravitational forces become infinitely strong at the singularity. It's a chilling thought, but also a profound illustration of the physical laws at play in the most extreme environments in the cosmos. The very fabric of reality, as we understand it, is being tested and reshaped in these cosmic laboratories. Spaghettification, therefore, is not just a dramatic name for a gruesome fate. It is a precise descriptor of the physical processes that occur when matter encounters the overwhelming power of a black hole. It's a stark reminder of the universe's capacity for both immense beauty and terrifying power, a power that can stretch the very essence of existence. And in this cosmic stretching, we are reminded that even our physical form is but a temporary arrangement, subject to the grand, indifferent forces of the universe. The inside might be a different universe entirely. Imagine for a moment that the very fabric of our reality, the familiar stage upon which all known phenomena play out, is not the only stage that exists. When we speak of the inside of a black hole, we are venturing into territory where our everyday understanding of space and time simply ceases to apply. Our current theories, our most sophisticated mathematical models, struggle to describe what lies beyond the event horizon, that ultimate cosmic boundary. But in this struggle, in this very breakdown of our familiar physics, lie some of the most mind-bending possibilities. One such possibility, born from the realm of theoretical physics, suggests that the interior of a black hole might not lead to a compressed point of infinite density, a singularity as traditionally envisioned. Instead, it could be a gateway, a cosmic portal to an entirely separate universe. This isn't just a fanciful notion. It arises from attempts to reconcile the seemingly incompatible worlds of general relativity, which describes gravity and large-scale structures, and quantum mechanics, which governs the subatomic realm. When two such massive and seemingly separate theories are pushed to their limits, particularly in extreme environments like the heart of a black hole, they can give rise to emergent phenomena that defy our intuition. Some theoretical frameworks propose that the singularity isn't a destination, but rather a transition. As matter and energy fall into a black hole, instead of being crushed into an infinitely dense point, they might be bounced, or repurposed, into the foundational elements of a new nascent universe. Think of it as a cosmic rebirth, where the remnants of one reality become the building blocks for another. This concept, while speculative, offers a profound perspective on the nature of existence. It suggests that the universe might be far more interconnected and cyclical than we ever imagined. The death of matter and energy in one universe could, in fact, be the birth of another. This idea challenges our linear perception of time and causality, hinting at a grander, more complex cosmic tapestry where universes are not isolated entities, but are perhaps woven together in ways we are only beginning to comprehend. The implications are staggering. If the inside of a black hole is indeed a gateway to another universe, then every black hole in our cosmos could be a cosmic incubator, a cradle for new realities. This would mean that the vast emptiness of space, dotted with these enigmatic objects, is also teeming with the potential for entirely new beginnings. Our own universe in this grand cosmic scheme might itself have originated from such a process, a descendant of a previous cosmic cycle. This perspective invites us to contemplate our place not just within our own universe, but within a potentially infinite multiverse, where the very laws of physics might vary from one reality to another. It's a humbling thought, one that expands our sense of wonder and diminishes the perceived isolation of our existence. The extreme conditions within a black hole, the very point where our current understanding falters, might be the very place where new universes are born, a testament to the universe's boundless capacity for creation and transformation. And so, the interior of a black hole, a place of ultimate mystery, may hold the promise of entirely new beginnings, a cosmic womb for realities yet unimagined. Ergosphere allows energy extraction from rotating black holes. Beyond the event horizon, where the very fabric of spacetime is irrevocably bent, lies another fascinating region for rotating black holes, a realm known as the ergosphere. Unlike the event horizon, which represents a one-way passage into the black hole, the ergosphere is a region where it is impossible to remain stationary relative to distant stars. Imagine standing on a treadmill that is moving so rapidly that no matter how fast you run, you are always being carried forward. This is a simplified, yet illustrative, analogy for the ergosphere. Within this region, spacetime itself is dragged along with the black hole's rotation at such a tremendous speed that anything caught within it is forced to rotate along with the black hole. Yet, crucially, it is still possible to escape the ergosphere if one has enough energy and follows a specific trajectory. This is where the profound concept of energy extraction comes into play, a process first theorized by physicist Roger Penrose. The Penrose process, as it is known, suggests that it is possible to extract rotational energy from a black hole by sending a particle into the ergosphere. This particle, when it enters the ergosphere, can be split into two. One of these fragments can then be directed to fall into the black hole, carrying with it negative energy relative to the outside universe. Because the total energy of the original particle must be conserved, the other fragment, which escapes the ergosphere, will carry away more energy than the original particle possessed. This means that the escaping fragment has gained energy, and this energy has been effectively siphoned from the black hole's rotational energy. This process does not violate the laws of physics. Rather, it demonstrates a remarkable consequence of extreme gravitational environments. The black hole's rotation, a vast reservoir of energy, can be tapped. The ergosphere, therefore, is not merely a boundary. It is a dynamic zone where the universe's most extreme object can, in a sense, be harnessed. It's a testament to the intricate dance between gravity, rotation, and energy, a cosmic engine with implications that stretch our understanding of what is possible. The energy extracted is not created from nothing. It is a direct consequence of the black hole's spin, gradually slowing it down over immense cosmic timescales. This process, while theoretical, offers a glimpse into the sophisticated mechanisms that govern the universe at its most extreme scales, revealing how even the most enigmatic celestial bodies can participate in the grand cosmic economy of energy. The ergosphere, therefore, is a region of immense scientific interest, a place where the seemingly impossible becomes a tangible possibility, a testament to the boundless ingenuity of the universe. It is a place where the very laws of physics, as we understand them, offer avenues for incredible phenomena, including the potential to tap into the immense power of a rotating black hole. The implications of this are far-reaching, suggesting that even in the most extreme environments, there are opportunities for energy to be exchanged and transformed, showcasing a universe that is both mysterious and elegantly governed by underlying principles, even when those principles manifest in ways that challenge our everyday intuition. The ergosphere represents a bridge between our current understanding and the profound unknowns that lie within the heart of a black hole, a region where the familiar rules of physics are stretched to their absolute limits, revealing new and unexpected possibilities. It highlights that the universe is not static, but is a dynamic interplay of forces and energies, and even objects as seemingly passive as black holes can be active participants in this cosmic dance of transformation and exchange. The ability to extract energy from a rotating black hole, though a complex theoretical concept, underscores the universe's capacity for surprising and elegant solutions to fundamental physical challenges, demonstrating that even in the face of overwhelming gravity, there are pathways for energy to be managed and transformed. This understanding deepens our appreciation for the intricate workings of the cosmos and the potential for phenomena that, at first glance, seem beyond our comprehension. In the dance of rotating gravity, even darkness can yield a spark of borrowed light. The Event Horizon Telescope captured the first black hole image. For eons, black holes remained theoretical specters, points of immense gravity so profound that they were forever hidden from direct observation. We could infer their presence through the dance of stars around invisible partners, or the violent feeding frenzies of matter spiraling into their depths. But the heart of the mystery, the very edge of their influence, remained elusive. Then, in a monumental feat of global scientific collaboration, humanity finally laid eyes on a black hole. The Event Horizon Telescope, or EHT, is not a single telescope, but a network of radio telescopes scattered across the Earth, working in unison. By employing a technique called Very Long Baseline Interferometry, or VLBI, these disparate observatories were linked together, creating an Earth-sized virtual telescope with an unprecedented resolution. This allowed them to peer into the cosmos with a sharpness previously unimaginable, to resolve details as fine as a donut on the moon. The target, the supermassive black hole at the center of the galaxy Messier 87, known as M87*. This colossal object, millions of times more massive than our Sun, resides at the heart of a galaxy over 50 million light-years away. The light reaching us from M87 has traveled for an immense duration, carrying within it a snapshot of this enigmatic entity. The image that emerged was not a stark, black void as one might initially imagine. Instead, it revealed a bright, incandescent ring surrounding a dark central region. This dark region, the shadow of the black hole, is precisely what we would expect if the light from the matter behind it is being so intensely warped by gravity that it bends around, or is captured by, the black hole itself. The bright ring is the emission from superheated gas and plasma swirling around the event horizon, heated to billions of degrees by the immense gravitational forces. The EHT team meticulously processed petabytes of data collected over several years, employing sophisticated algorithms to reconstruct the image, overcoming the challenges of atmospheric distortion and the sheer distance involved. It was a triumph of engineering, physics, and international cooperation, a testament to our unyielding curiosity to understand the universe's most extreme phenomena. This captured image provided the first direct visual evidence that the seemingly abstract concepts of general relativity, particularly the existence of event horizons, manifest in the real universe. It confirmed that the universe behaves according to these profound mathematical descriptions, even in its most violent and mysterious corners. The image of M87*'s shadow is more than just a photograph. It is a confirmation of our understanding of gravity at its most extreme, a visual anchor for the theoretical frameworks that have guided our cosmic exploration. It is a bridge between the abstract and the observable, a moment when the invisible became visible and the distant became intimately known. The black hole, once a mere mathematical curiosity, was rendered tangible, a celestial object whose shadow we could finally see. This achievement opened a new window into the study of black holes, allowing scientists to probe their properties with unprecedented detail and to test the limits of our current physical theories. The faint glow captured across the vast expanse of space serves as a beacon of human ingenuity, illuminating the profound mysteries that lie at the very fabric of reality. The first image of a black hole's shadow is a cosmic whisper, confirming that even in the deepest darkness, there is a profound, observable order that speaks to the quiet grandeur of existence. Accretion disks are superheated matter orbiting the hole. Imagine a celestial whirlpool, a swirling vortex of cosmic dust and gas drawn inexorably towards the gravitational maw of a black hole. These are the accretion disks, and they are not merely passive bystanders in the black hole's existence, but rather a vibrant, energetic, and intensely luminous testament to its power. As matter, whether it be stray gas from interstellar clouds, or the shredded remains of a star unfortunate enough to wander too close, approaches a black hole, it doesn't simply plunge directly in. Instead, due to the conservation of angular momentum, it begins to orbit. This orbital motion, however, is not a gentle ballet. The immense gravitational pull of the black hole, combined with the sheer speed of the orbiting material, causes friction. This friction, on a scale almost incomprehensible to us, heats the matter to extraordinary temperatures. We're talking about millions, even billions of degrees Celsius, hot enough to ionize the gas, stripping electrons from their atoms and creating a superheated plasma. This plasma glows intensely across the electromagnetic spectrum, from radio waves to visible light, and most powerfully in X-rays. It is this incandescent glow from the accretion disk that often allows us to detect black holes, even though the black hole itself remains invisible. The material within the disk doesn't orbit at the same speed. The inner regions, closer to the event horizon, move much faster than the outer regions. This differential rotation further exacerbates the friction, converting gravitational potential energy into kinetic energy, and then, through collisions and turbulence, into heat. The disk is not a uniform, flat disk. It's a complex, dynamic structure, often with outflows and jets of plasma being ejected from the poles, driven by magnetic fields amplified within the disk itself. These jets can travel at nearly the speed of light, extending for vast distances into space, influencing the evolution of galaxies. The process of matter falling into a black hole via an accretion disk is one of the most efficient energy conversion mechanisms known in the universe. More efficient, in fact, than nuclear fusion, the process that powers stars. This efficiency means that the accretion disks around black holes can be incredibly luminous, outshining the combined light of all the stars in their host galaxies. Studying these disks allows us to probe the extreme physics near the event horizon, to understand how black holes grow, and to witness the raw power of gravity in action. The light we see from an accretion disk is a snapshot of matter on its final, fiery descent, a cosmic spectacle painted in incandescent hues. It's a reminder that even in the deepest, darkest voids, there can be an astonishing display of energy and light, a testament to the universe's boundless creativity and destructive potential. The very act of matter being consumed creates its own brilliant farewell. In the fiery embrace of the accretion disk, the universe whispers its most intense secrets, a luminous farewell before the silence. Gravitational lensing distorts light from distant objects. Imagine the fabric of spacetime, not as an empty void but as a vast, invisible tapestry. Now picture a heavy object like a massive galaxy or, even more profoundly, a black hole placed upon this tapestry. Its immense gravity causes the fabric to warp and curve, creating a dimple, a distortion. This is the essence of gravitational lensing. When light from a distant star or galaxy travels towards us, it doesn't simply move in a straight line. Instead, it follows the contours of this warped spacetime. As it passes near a massive object, its path is bent, much like a ray of light passing through a glass lens. This bending of light can have several fascinating effects. For us, observing from Earth, it can make distant objects appear brighter, magnified, or even appear in multiple locations. A single distant galaxy might be seen as 2, 3, or even a complete ring of light, known as an Einstein ring, if the alignment is perfect. This phenomenon is not just a curious optical illusion, it's a powerful tool for astronomers. By studying how light is lensed, scientists can map the distribution of mass in the universe, including the invisible dark matter that constitutes a significant portion of its mass. They can also use gravitational lensing to study the most distant and faint galaxies, whose light would otherwise be too dim to detect. The way a black hole warps spacetime is so extreme that it can bend light around itself, creating intricate patterns and distortions that reveal its presence and the nature of its gravity. It's as if the universe itself is acting as a cosmic magnifying glass, revealing secrets hidden across vast cosmic distances. The light, bent and reshaped by the unseen hand of gravity, carries with it a story, a testament to the immense forces at play in the cosmos. This distortion isn't a flaw in our view, but a fundamental aspect of how light navigates the universe, shaped by the very presence of matter and energy. It allows us to peer into the deep past, to see galaxies as they were billions of years ago, their light having traveled across unimaginable gulfs of space and time, its journey guided by the invisible architecture of gravity. The distortion is not merely a visual effect. It's a profound revelation about the interconnectedness of mass, energy, and the very geometry of existence, a constant reminder that what we perceive as straight lines are, in fact, elegant curves sculpted by the universe's grand design. The bending of light, therefore, is not an aberration but a fundamental characteristic of reality, a cosmic ballet choreographed by gravity itself, revealing the unseen architecture of the cosmos and the profound influence of massive objects on the journey of light across the universe, offering us a unique and awe-inspiring perspective on the vastness and complexity of the cosmos. The light bends, revealing the universe's hidden mass, a cosmic whisper of gravity's grand, unseen hand. Black holes can evaporate over vast cosmic timescales. For a long time, black holes were thought to be eternal, forever consuming matter and energy, their immense gravity an insurmountable force that would endure for all of time. This perception, while intuitive given their nature, overlooks a subtle yet profound aspect of quantum mechanics that Stephen Hawking brilliantly unveiled. He proposed that black holes are not entirely black, but rather emit a faint thermal radiation, now known as Hawking radiation. This radiation arises from quantum fluctuations near the event horizon. Imagine the vacuum of space not as empty, but as a sea of fleeting virtual particles that pop into existence and then annihilate each other almost instantaneously. Near the event horizon, however, it's possible for one of these virtual particles to fall into the black hole while its partner escapes. To an outside observer, it appears as if the black hole is emitting particles. These escaping particles carry away a tiny amount of energy, and since energy and mass are equivalent according to Einstein's famous equation, E = mc2, this means the black hole is losing mass. The process is incredibly slow for stellar mass black holes, far slower than the current age of the universe. A black hole with the mass of our Sun, for instance, would take an unfathomably long time to evaporate, around 10 to the power of 67 years. For supermassive black holes found at the centers of galaxies, this timescale stretches even further, to perhaps 10 to the power of 100 years. However, for much smaller hypothetical black holes, perhaps formed in the early universe, this evaporation process could be much more rapid, potentially even leading to a final, dramatic burst of energy. This concept of black hole evaporation fundamentally alters our understanding of these cosmic entities, suggesting that even the most seemingly permanent structures in the universe are subject to change and eventual dissolution. It paints a picture of a universe in constant dynamic flux, where even the deepest gravitational wells are not immune to the subtle whispers of quantum reality, slowly, over eons, releasing what they have consumed back into the cosmos. Even in the deepest darkness, change finds a way to bloom across the endless canvas of time. The universe's expansion might be driven by dark energy, similar to black hole dynamics. Imagine, for a moment, the vast, silent expanse of the cosmos. We perceive it as a grand, ever-expanding tapestry, a cosmic ballet choreographed by forces we are only beginning to comprehend. One of the most profound enigmas in modern cosmology is the accelerating expansion of the universe, a phenomenon attributed to a mysterious entity known as dark energy. While seemingly distinct from the inward pull of a black hole, the underlying principles governing these extreme cosmic structures might share a surprising kinship, offering us a new lens through which to view the universe's grandest movements. Black holes, as we've explored, represent regions of spacetime where gravity is so intensely concentrated that nothing, not even light, can escape. Their immense gravitational influence warps the very fabric of reality around them. Now, consider the universe as a whole. For decades, astronomers believed that the expansion, initiated by the Big Bang, should be slowing down due to the gravitational pull of all the matter within it. However, observations, particularly those of distant supernovae in the late 1990s, revealed something astonishing. The expansion isn't slowing down, it's actually speeding up. This acceleration implies the existence of a repulsive force, counteracting gravity on a cosmic scale, and this force is what we call dark energy. The nature of dark energy remains one of the greatest unsolved puzzles in physics. It's estimated to constitute about 70% of the total energy density of the universe, yet we know very little about its origin or its properties. One leading hypothesis is that dark energy is a property of space itself, an intrinsic energy that permeates the vacuum. As the universe expands, more space is created, and thus more of this inherent energy comes into being, driving further expansion. This concept, known as the cosmological constant, was originally proposed by Albert Einstein, though he later famously called it his biggest blunder when the universe was thought to be static. Now, it seems, his initial intuition might have been closer to the truth than he realized. Another perspective suggests that dark energy could be a dynamic field, evolving over time, much like other fundamental fields in physics. This quintessence model offers more flexibility than the cosmological constant, potentially explaining variations in the expansion rate throughout cosmic history. Regardless of the specific model, the effect is the same: a pervasive pressure pushing spacetime apart. Now, how might this relate to black holes? While black holes are characterized by their overwhelming inward gravitational force, they also represent extreme distortions of spacetime. The event horizon, the boundary beyond which escape is impossible, is a manifestation of this extreme curvature. Some theoretical frameworks, particularly those exploring quantum gravity and alternative models of spacetime, hint at connections between the physics of black holes and the large-scale dynamics of the universe. For instance, in certain theoretical models, the geometry of spacetime near a black hole can exhibit behaviors that, when scaled up to cosmic proportions, bear resemblance to the expansion of the universe. The idea is that the emptiness of space, far from being truly empty, might possess an inherent energy density. This energy density, much like the energy associated with the vacuum in quantum field theory, could exert a negative pressure, leading to an outward push. Consider the analogy of a stretched rubber sheet. A heavy ball placed on the sheet creates a dip, representing the warping of spacetime by mass, like in a black hole. However, if the sheet itself had a tendency to expand, to push outwards, that would be akin to dark energy. The interplay between the local warping by matter and the global tendency of spacetime to expand is what defines the cosmic evolution we observe. Furthermore, some speculative theories propose that the universe might be a kind of emergent phenomenon arising from the collective behavior of black holes, or that our universe could even be contained within a larger, higher-dimensional space, with cosmic expansion being a consequence of our surface interacting with this higher dimension, a concept reminiscent of holographic principles often discussed in black hole physics. The implications of dark energy are profound. It dictates the ultimate fate of the universe. If dark energy remains constant, the universe will continue to expand at an accelerating rate, leading to a big freeze or heat death, where galaxies become increasingly distant and isolated, and eventually all stars burn out. If dark energy were to increase in strength, it could lead to a big rip, where the expansion becomes so powerful it tears apart galaxies, stars, planets, and even atoms themselves. While the precise mechanism is still elusive, the concept of an inherent energy within spacetime, driving expansion, offers a profound philosophical parallel to the extreme gravitational influence of black holes. Both phenomena highlight the dynamic, malleable, and often counterintuitive nature of the universe's fundamental structure. They remind us that what we perceive as empty space is, in fact, a vibrant, energetic medium, constantly shaping and reshaping reality on the grandest scales. The universe's relentless outward push, driven by this enigmatic dark energy, is a cosmic breath, a grand exhalation that shapes the destiny of all that exists within its boundless embrace. Our perception of reality is shaped by our local spacetime. Imagine standing on a vast, flat plain. The horizon stretches out, seemingly infinite, and the ground beneath your feet feels solid and unchanging. This is your local spacetime, the immediate fabric of existence that your senses interpret as reality. It's a familiar, comfortable space where the rules of physics, as you experience them, are consistent and predictable. We move through this space, our bodies obeying the laws of motion, our minds processing information as it arrives in a linear, sequential fashion. The passage of time feels constant, a steady river flowing from past to future. Our perception of distance, of speed, of the very nature of things is deeply rooted in this immediate local experience. We build our understanding of the universe, our place within it, and our interactions with others based on these fundamental, everyday observations. This local spacetime is our anchor, the frame of reference against which all other phenomena are measured. It's the stage upon which our lives unfold, and its perceived stability is crucial for our sense of order and comprehension. However, as we've explored the extreme environments of black holes, we've begun to understand that this seemingly immutable stage is, in fact, a far more flexible and dynamic entity than we might intuitively grasp. The very way we perceive now, the duration of a moment, the spatial relationships between objects, are not absolute truths but rather consequences of the gravitational field we inhabit. Our local spacetime, with its familiar laws, is a specific manifestation of a much grander and often stranger cosmic architecture. It's like a single note played on a grand organ, a beautiful sound in itself, but only a small part of a much larger symphony. The curvature of spacetime, dictated by the distribution of mass and energy, directly influences how we experience the universe. Where gravity is weak, spacetime is nearly flat, and our perceptions align with what we consider common sense. But as gravity intensifies, as it does near a black hole, this common sense begins to unravel. The very concepts of up and down, forward and back, can become distorted, even meaningless, depending on your proximity to such immense gravitational wells. This is not just a theoretical curiosity. It has tangible implications for how we understand the universe at its most fundamental levels. For instance, The speed of light, often considered a universal constant, is perceived differently depending on the observer's gravitational environment. While its local speed remains constant, its trajectory and the time it takes to traverse distances can be dramatically altered by the warping of spacetime. This means that two observers, each experiencing their own local spacetime, might disagree on fundamental measurements of distance and time, even though both are operating within the framework of the same physical laws. This relativity of perception is a cornerstone of Einstein's theories and highlights the profound connection between gravity and our experience of reality. It suggests that our everyday understanding of the universe, while perfectly functional within our local context, is a limited perspective. The universe is not simply a collection of objects existing in a void. It is a dynamic interplay of matter, energy, and the very fabric of spacetime itself. Our perception is, therefore, not a passive reception of objective reality, but an active interpretation shaped by the gravitational landscape we inhabit. This realization can be both humbling and liberating. It reminds us that our current understanding is a snapshot, a particular view from our unique vantage point in the cosmic tapestry. The vastness of the universe, with its myriad gravitational environments, suggests an infinite spectrum of possible perceptions, a universe of realities far richer and stranger than our local experience might suggest. The implications extend to our understanding of causality and the flow of events. In regions of extreme spacetime curvature, the very notion of cause and preceding effect can become blurred. What one observer perceives as a sequence of events, another, in a different gravitational frame, might perceive as simultaneous or even reversed. This challenges our deeply ingrained linear view of time and underscores how profoundly our local spacetime dictates our understanding of how the universe unfolds. It's a reminder that our common sense is a highly localized phenomenon, finely tuned to the specific conditions of our corner of the cosmos. The illusion of a stable, absolute reality is, in a sense, a product of our relatively placid gravitational environment. The more we explore the extremes, the more we realize that the universe is not built to conform to our intuitive expectations, but rather to operate according to principles that can, at times, seem utterly alien. This ongoing exploration, this journey into the heart of black holes and the nature of spacetime, is ultimately a journey into the very foundations of our own perception and our place within the grand cosmic order. It's a testament to the power of human curiosity to probe the deepest mysteries of existence and to expand our understanding of what reality truly is, beyond the confines of our immediate experience. The universe, in its most extreme manifestations, forces us to confront the limitations of our senses and the profound influence of gravity on our perception of everything. Our local spacetime crafts the very stage upon which our reality is perceived, a gentle reminder that our understanding is but one perspective in a universe of infinite possibility. The center of our own galaxy hosts a supermassive black hole. At the very heart of our Milky Way galaxy, nestled within the dense, swirling cosmic ballet of stars and gas, lies an entity of such profound power and mystery that it both humbles and awes us. This is Sagittarius A, or SGR-A for short, a supermassive black hole, a celestial titan whose gravitational embrace governs the motions of billions of stars. For a long time, the galactic center was an enigma, shrouded in dust and obscured by the sheer density of stars, making direct observation incredibly challenging. However, through decades of meticulous observation, utilizing cutting-edge telescopes that can pierce through this cosmic veil, astronomers have pieced together a compelling picture. They've tracked the precise orbits of stars moving at astonishing speeds, whipping around an invisible point with incredible velocity. These stellar velocities, when analyzed through the laws of gravity, can only be explained by the presence of an object with an immense mass concentrated in an incredibly small volume. This object, SGRA, is estimated to have a mass equivalent to about 4 million suns, all packed into a region not much larger than our solar system. The very existence of such a massive object at the galactic core is a testament to the universe's capacity for creating extreme phenomena. It's not just a gravitational anchor, it's a dynamic engine, influencing the evolution of the entire galaxy. The superheated gas and dust that orbit SGRA form an accretion disk, a swirling, incandescent whirlpool of matter being drawn inexorably towards the black hole. This disk glows intensely across various wavelengths of light, from radio waves to X-rays, providing crucial clues about the black hole's activity. While the black hole itself is invisible, its presence is undeniably felt through its profound gravitational influence and the energetic phenomena it orchestrates. The study of SGRA is not just about understanding a single object. It's about understanding the fundamental processes that shape galaxies, how they form, how they grow, and how they interact with their surroundings. It offers a tangible, albeit distant, glimpse into the extreme physics that governs our cosmic home. The sheer scale of this central black hole reminds us of the vastness of the universe and the intricate, often invisible forces that orchestrate its grand design. It is a silent, colossal presence, the ultimate anchor of our galactic neighborhood, a constant reminder of the universe's boundless power and the enduring quest to comprehend it. The precise measurements of stellar orbits, the detection of radio emissions, and the long, patient observations have all converged to paint a picture of this incredible, unseen force at the very heart of everything we know. It's a place where the most extreme conditions in the universe are not just theoretical, but a living, breathing reality, shaping the destiny of our galaxy. It's a fascinating paradox. The most powerful object in our galaxy is also the most elusive, a testament to the profound mysteries that still lie at the core of our cosmic home. Even in the familiar embrace of our own galaxy, the universe whispers tales of immense power, reminding us that even the most stable homes are anchored by the unseen, the profound, and the eternally mysterious. Black holes play a crucial role in galaxy formation. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These cosmic giants, millions or even billions of times the mass of our Sun, are not merely passive inhabitants but active participants in the grand ballet of galactic evolution. Their influence extends far beyond their immediate vicinity, shaping the very structure and growth of the galaxies they reside within. Imagine a celestial engine, a gravitational dynamo that, through a complex interplay of forces, guides the distribution of stars, gas, and dark matter across vast cosmic distances. The relationship between a supermassive black hole and its host galaxy is often described as coevolution. This means they grow and change together, each influencing the other's development over billions of years. When gas and dust fall towards a black hole, they don't plunge directly in. Instead, they form a swirling, superheated disk called an accretion disk. As this material spirals inwards, friction and gravitational forces heat it to incredible temperatures, causing it to emit vast amounts of energy across the electromagnetic spectrum, from radio waves to X-rays. This energetic outflow, known as an active galactic nucleus, AGN, or a quasar when at its most luminous, can have a profound impact on the surrounding galaxy. These powerful outflows, often in the form of jets of plasma ejected at near-light speeds, can heat, or expel the cooler gas within the galaxy. This gas is the very fuel required for star formation. By pushing this gas away or making it too hot to condense into stars, the black hole can effectively regulate or even shut down star formation in its host galaxy. This feedback mechanism is crucial for explaining why many massive galaxies have stopped forming stars and appear red and old, rather than blue and actively forming new stellar generations. Without this regulation, galaxies might continue to grow indefinitely, accumulating far more stars than we observe. Furthermore, the gravitational pull of the supermassive black hole influences the orbits of stars and gas clouds in the galactic center, contributing to the formation of galactic bulges and bars. It can also channel gas towards itself, providing the very sustenance that allows it to grow and, in turn, to exert its influence on the larger galaxy. This delicate balance between inflow and outflow, growth and regulation, is a testament to the intricate, interconnected nature of the cosmos. The presence of these colossal gravitational wells at galactic centers is not an anomaly, but a fundamental aspect of how galaxies come to be the majestic structures we observe across the universe. They are the architects of galactic destiny, silently, powerfully, guiding the formation and evolution of entire stellar civilizations. And so, the colossal heart of a galaxy beats in rhythm with its stellar kin, a silent, powerful force shaping the cosmic tapestry. The concept of nothingness is complex in a black hole. When we speak of nothingness, our minds often conjure images of emptiness, a void devoid of matter, energy, and even space itself. It's a concept that, in our everyday experience, signifies absence. But within the extreme environment of a black hole, this familiar notion of nothingness undergoes a profound and bewildering transformation. The very fabric of reality, as we understand it, unravels, leading us to question what nothing truly means when the rules of existence are so drastically rewritten. Consider the event horizon. From the outside, it appears as a boundary, a cosmic membrane beyond which all information, all matter, and all light are irrevocably lost. Yet, for an object or observer falling through this boundary, there is no immediate sensation of hitting a wall or entering a void. The transition can, in fact, be surprisingly smooth, at least initially. This is where the complexity begins. The nothingness inside is not an absence of everything, but rather a realm where the very concepts of everything and nothing become indistinguishable or perhaps simply irrelevant. Our classical understanding of space and time, which forms the bedrock of our intuition about emptiness, breaks down catastrophically at the singularity. Here, matter is compressed to an infinitely small point of infinite density. This is not a void. It is an extreme concentration of everything compressed beyond our current comprehension. The nothingness we perceive from afar is, in a sense, a consequence of this ultimate condensation. It is the absence of observable phenomena outside the black hole, not necessarily an absence of existence with an asterisk. Furthermore, quantum mechanics introduces another layer of complexity. While general relativity suggests a singularity, quantum gravity, the yet-to-be-unified theory that aims to reconcile these two pillars of physics, hints at different possibilities. Some theories propose that the singularity might not be an infinitely dense point, but rather a region of extreme quantum fluctuations, a fuzzball of exotic particles and energies. In this scenario, nothingness is replaced by an incredibly energetic and complex quantum state, far removed from any intuitive idea of emptiness. The information paradox also plays a role. If information truly disappears into a black hole, as classical physics suggests, then the universe would be fundamentally non-deterministic, a concept that deeply unsettles physicists. The proposed solutions, such as Hawking radiation carrying information away, or the holographic principle suggesting information, is encoded on the event horizon, further complicate the idea of a simple void. They imply that even in what appears to be the ultimate nothing, there might be an intricate, albeit hidden, form of existence. Ultimately, the nothingness inside a black hole is not a passive absence, but an active participant in the extreme physics of these cosmic objects. It is a conceptual frontier where our everyday definitions fail, forcing us to confront the limits of our understanding and the profound mysteries of the universe. It is a place where the absence of familiar structures might, paradoxically, be filled with an unimaginable density of reality itself, a reality so alien that our language for nothing simply cannot grasp it. Within the crushing embrace of a black hole, the void is not empty, but a testament to the universe's most profound and enigmatic truths. What lies beyond the event horizon remains a profound mystery. The boundary we call the event horizon is, in essence, a veil. It's a cosmic curtain beyond which our current instruments, our current understanding, and indeed our very laws of physics, cease to provide us with a clear, verifiable picture. Imagine standing at the edge of a waterfall, the roar of the water a deafening symphony, the mist a blinding shroud. You can see the precipice, the point of no return, but what unfolds in the churning depths below, what happens to the water as it plunges into the unknown, is something you can only infer, not directly observe. This is the nature of the event horizon. It is not a physical surface, not a solid wall, but a conceptual boundary defined by the inescapable pull of gravity. Once anything, be it a particle of light or a daring spacecraft, crosses this threshold, its fate is sealed, and its journey into the interior becomes a one-way trip. The very fabric of spacetime, as we understand it, is so intensely warped within this region that our familiar notions of space and time begin to dissolve. The singularity, a point of infinite density predicted by classical general relativity, lies somewhere within, but even its existence and nature are subjects of intense debate, particularly when quantum effects are considered. Some theories propose that the singularity might not be a point at all, but rather a more complex structure, perhaps a region where spacetime itself is fundamentally reconfigured. Others suggest that the information carried by the infalling matter might not be truly lost, but rather encoded in some exotic way, perhaps on the event horizon itself, or in the subtle quantum fluctuations that permeate the region. The extreme gravitational forces at play mean that, for an observer falling into a black hole, time would appear to slow down dramatically from the perspective of someone watching from a safe distance. However, for the infalling observer, time would continue to pass normally until they reach the singularity. But what happens at the singularity? Does matter get crushed into an infinitely small point? Does it transition into another form? Or does it perhaps enter a different universe, a cosmic portal to realms beyond our comprehension? These are the questions that push the boundaries of our scientific imagination. The very act of trying to describe what lies beyond the event horizon forces us to confront the limitations of our current models. We are at the frontier of knowledge, where the familiar rules of the cosmos bend and break, and where profound philosophical questions about the nature of reality, existence, and the universe itself arise. It is a testament to the vastness and mystery of the cosmos that even in the most extreme environments, there remain realms that are, for now, beyond our direct grasp, inviting us to ponder the unimaginable. Beyond the veil of the event horizon lies a realm where our certainties dissolve, leaving us with the quiet wonder of the unknown. The universe continues to surprise us with its extremes. The cosmos, in its boundless expanse, consistently unveils phenomena that stretch the very limits of our comprehension, and perhaps even our imagination. Black holes, those enigmatic entities at the heart of our discussion, stand as prime examples of these cosmic extremes. They are not merely theoretical constructs. They are physical realities that challenge our most fundamental understandings of space, time, gravity, and matter. Consider the sheer density involved. Within the event horizon of a black hole, a mass equivalent to several suns, or even billions of suns for supermassive black holes, is compressed into an infinitesimally small point, the singularity, or perhaps something even more exotic. This is an extremity of density that our everyday experiences can scarcely grasp. Our world is governed by forces and scales that allow for a certain degree of predictability, a comforting familiarity. But the universe, in its grand theater, presents us with stages where these familiar rules seem to bend, warp, and even shatter. The gravitational pull of a black hole is so immense that it dictates the very fabric of spacetime around it. Imagine spacetime as a stretched rubber sheet. A massive object like a star creates a dimple. A black hole, however, creates a chasm, a tear in the fabric itself. This extreme warping means that light, the fastest thing in the universe, cannot escape its clutches once it crosses a certain boundary, the event horizon. This boundary itself is a profound surprise. It's not a physical surface you can touch, but a conceptual one, a point of no return defined by gravity. And the effects on time are equally astonishing. According to Einstein's theory of relativity, time is not absolute but is interwoven with space, forming spacetime. Near a black hole, where gravity is at its most extreme, time itself slows down relative to an observer far away. For an astronaut venturing close to the event horizon, seconds might feel like minutes, hours, or even years to those observing from a safe distance. This temporal dilation, this stretching of time, is a direct consequence of the universe's capacity for extreme gravitational conditions. Furthermore, the very act of approaching a black hole can lead to a phenomenon known as spaghettification. The gravitational pull on the part of an object closer to the black hole is significantly stronger than the pull on the part further away. This differential force would stretch an object, like a hypothetical astronaut, into a long, thin strand, much like spaghetti. It's a stark and dramatic illustration of how extreme gravity can distort physical forms. Even the concept of what a black hole is continues to evolve, presenting further surprises. While the singularity was once thought to be the inevitable endpoint, newer theories suggest possibilities like fuzzballs, complex quantum structures, or even gateways to other universes. These ideas, born from the intersection of quantum mechanics and general relativity, reveal the limitations of our current models when faced with these cosmic extremes. The universe, it seems, is always one step ahead, constantly pushing the boundaries of our understanding and reminding us that what we perceive as reality is but a snapshot of its vast and often bewildering potential. The discovery of phenomena like gamma-ray bursts, the most powerful explosions in the universe, or the sheer scale of cosmic voids, vast regions of space containing very few galaxies, further underscore this point. Each new observation, each theoretical breakthrough, adds another layer to the intricate tapestry of cosmic surprise. The universe does not shy away from the extraordinary. It embraces it, weaving it into the very structure of existence. And in this constant unveiling of the extreme, we find not just intellectual stimulation, but a profound sense of wonder that can help us contextualize our own place within this magnificent and sometimes overwhelming cosmic drama. The universe's capacity for extremity is a testament to its infinite creativity, a reminder that the most profound truths often lie just beyond the edge of our current perception. In the grand cosmic theater, where familiar rules bend and shatter, the universe's extremes remind us that our understanding is but a whisper against the roar of its boundless, surprising existence. Our quest for knowledge illuminates the unknown. The pursuit of understanding, of unraveling the universe's deepest secrets, is a defining characteristic of our existence. It is a journey that stretches back to the earliest flicker of human consciousness, a persistent urge to look beyond the immediate, to question the nature of reality itself. When we turn our gaze towards the enigmatic depths of a black hole, we are not merely observing a celestial object. We are engaging in one of the most profound quests imaginable. This quest is not about conquering the unknown, but about illuminating it, about bringing the gentle light of reason and observation to bear upon the absolute darkness. Even if we can never truly enter a black hole in the physical sense, the very act of studying them, of formulating theories and designing experiments, pushes the boundaries of our comprehension. It forces us to invent new mathematics, to refine our understanding of fundamental forces, and to confront the limits of our current scientific models. The information we gather, the patterns we discern, the elegant equations that attempt to describe these extreme environments, these are the lights we cast into the void. Each discovery, no matter how small, adds a tiny spark to the vast canvas of what we do not know. This process of scientific inquiry, this relentless questioning, transforms the terrifying abyss of the unknown into a landscape of fascinating, albeit challenging, exploration. It is a testament to the human spirit's capacity for wonder and its unwavering desire to comprehend its place within the grand cosmic tapestry. The very act of seeking knowledge about these ultimate enigmas, like black holes, reveals not just the nature of the universe, but also the extraordinary potential of our own minds to grapple with its most profound mysteries. It is through this illuminated quest that we find not fear, but a quiet awe, a sense of connection to something far greater than ourselves. The pursuit itself, the intellectual journey into the heart of darkness, becomes a source of profound perspective, reminding us that even in the face of ultimate unknowability, the light of human curiosity can still find its way. This illumination, this bringing of understanding to the enigmatic, is a deeply soothing and perspective-altering endeavor, a balm for the anxious mind. In the endless expanse, our curiosity is the gentle dawn that begins to reveal the shape of the deepest night. Embracing the mystery offers a sense of peace. The universe, in its grand and intricate tapestry, often presents us with phenomena that stretch the very limits of our comprehension. Black holes, with their enigmatic interiors and the profound warping of spacetime they represent, are perhaps among the most compelling examples of this cosmic mystery. We have delved into the mathematical frameworks, the observational evidence, and the theoretical possibilities. Yet the absolute truth of what lies beyond the event horizon, what the singularity truly signifies, remains elusive. This inherent unknowing, this vast expanse of what we do not yet understand, can, paradoxically, become a source of profound peace. Instead of wrestling with the frustration of unanswered questions, we can choose to marvel at the sheer scale of existence and the boundless potential for discovery. It is in acknowledging the limits of our current knowledge, in accepting that some cosmic secrets may be beyond our immediate grasp, that we can begin to find solace. This acceptance is not a surrender to ignorance, but a profound act of intellectual humility. It allows us to release the pressure to have all the answers, to let go of the anxiety that can arise from confronting the unknown. Imagine the vastness of the cosmos, a canvas painted with stars, galaxies, and indeed black holes, each a testament to forces and principles far grander than our individual understanding. To be a part of this immense and mysterious universe, to be able to contemplate its deepest secrets, even if we cannot fully unravel them, is a privilege. This perspective shifts our focus from the personal struggle for certainty to a shared wonder at the magnificent spectacle of reality. When we embrace the mystery of what lies inside a black hole, we are not diminishing its scientific significance, but rather elevating our own capacity for awe. We are recognizing that the universe is not a puzzle to be solved completely, but an ongoing, unfolding marvel to be experienced. This acceptance allows the mind to quiet, to cease its anxious striving for concrete answers, and to instead settle into a state of peaceful contemplation. The questions themselves, when approached with a sense of wonder rather than desperation, become pathways to a deeper appreciation of existence. The very fact that such profound enigmas exist is, in itself, a testament to the universe's inexhaustible creativity. By letting go of the need for definitive knowledge about the black hole's interior, we open ourselves to a more profound connection with the cosmos. We become observers, not just of facts and figures, but of the breathtaking, ongoing revelation of reality. This embrace of the unknown is a gentle surrender, a quiet acknowledgement that the universe is far more complex and wondrous than our current minds can fully contain. And in that surrender, in that quiet contemplation of the vast, unfathomable depths, we find a profound and lasting peace, a sense of belonging to something so much larger than ourselves, a stillness that allows the weary mind to finally rest. The greatest peace is found not in knowing all, but in marveling at the beautiful unknown. Our calm exploration has covered the profound mysteries held within the enigmatic embrace of a black hole. We've journeyed from the inescapable boundary of the event horizon to the theoretical breakdown of physics at the singularity, witnessing how spacetime itself warps and bends under the immense gravitational pull. We've touched upon the mind-bending concepts of time dilation, tidal forces, and the surprising revelation of Hawking radiation, which suggests these cosmic voids might not be entirely dark after all. We've pondered the information paradox, the intriguing idea of fuzzballs, and how our very understanding of inside dissolves into a realm where the familiar laws of physics no longer apply. Tonight, we have reviewed the principles of extreme gravity, the limits of our current scientific understanding, and the philosophical implications that arise when we confront the universe's most powerful and perplexing phenomena. The illusion of spacetime, a concept that governs our everyday reality, is dramatically altered, even dissolved within the heart of a black hole. Yet, in this dissolution, we find not chaos, but a deeper appreciation for the intricate tapestry of existence. Consider that the very fabric of reality, the spacetime we inhabit, is a delicate dance of forces. The black hole, in its ultimate expression of gravity, is a cosmic reminder of this profound interconnectedness, a celestial phenomenon that bends not just light and time, but also our perspective on our own place within this grand, awe-inspiring universe. Just as an object is stretched and distorted by tidal forces, our worries and anxieties can, with a shift in perspective, be rendered less significant against the backdrop of such cosmic immensity. As you rest, allow these thoughts to gently settle like stardust in the quiet expanse of night. You are a part of this universe, a universe that holds such breathtaking wonders and profound mysteries. There is no need to hold onto the day's stresses. They are temporary, fleeting, much like the journey of a photon near a black hole. It is time to release them, to drift into the vast, peaceful unknown of sleep. Sleep well, good night. It is time to rest now. If you happen to still be awake, you can drift into the next chapter now, continuing this journey of quiet wonder.